The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, good morning, and welcome to our webinar on Big Data Let's Mac. I would say we'll wait for like 2 or 3 more minutes for more people to join, but then we're good to go. Feel free to already ask questions up front or note anything you would like to say or have covered in this webinar. So now I guess we can get started. I hope some more people will join, but they can also catch up, and there will also be a recording later on. So let's hit play and get started. This webinar is actually kind of a teaser for the Code Motion conference. Well, I actually also will speak in Milan early November, so it's like about a month from now. So if you want to learn more about DCUS and a lot of other exciting topics, I just checked out the schedule this morning and I'm really excited to be one of the speakers. Yeah, come to Milan. At Milan, I'm actually going to talk about no one puts Java in a container. And that's actually a topic which is very dear to me as well, similar as the Smack Stack, which we're going to cover today. But it's basically about what you should be aware of when you're containerizing your applications, and especially what you should be aware of when containerizing your Java applications. If you're checking out the Java 9 standard, for example, there has been done a lot to better support the Java/JVM running in containers, but there are still a number of pitfalls. So if you want to learn more about this, come to Milan and listen to our talk about no one puts Java in a container. But for today, we're actually going to talk about a different topic, and this is a Smack Stack. In this case, this is me. I'm Jorg. I'm a software engineer here at Mesosphere in San Francisco. We're still very early this morning, but I hope I'll be awake enough for this webinar. And what is this about? So in ancient times, big data was actually very simple because we had just MapReduce crunching the data from a setup. You had one big MapReduce cluster somewhere down in your basement, and that was actually dedicated to Hadoop, and everything was good. Unfortunately, today it's a little different, the picture, and it's mostly that we need to turn faster. MapReduce, it's was great in crunching like this batch style processing, where I would collect a lot of data, and at the end of a week, at the end of the day, I would spin off one batch job, which would actually compute all the data. And response times didn't matter too much. They were usually, depending on the data size, somewhere in the hours, sometimes even up to like a day or so, as said, depending on the data size. Today, this is slightly different, and today we have a lot of use cases for so-called fast data processing. And let's just see what can be meant by that. On the left, we see still the traditional batch style processing, where we have response time somewhere in the range of days to hours. And there's still use cases where we can utilize that. So for example, if we do billing at the end of the month, it's typically something where we don't worry too much about response times. But more likely, we want to have response time somewhere in the range of minutes to seconds. And this is what we usually refer to as micro-batching. And this is, for example, if I want to display product recommendations or somewhere close to real-time pricing or routing information somewhere on my website. There, I don't want to wait a day to update the product recommendations. This fortunately works a little quicker nowadays. Still, there are use cases which even require faster processing. So imagine, for example, my credit card. If I use my credit card over here in San Francisco, I don't want to wait for a minute or even 2-3 seconds to wait until it's approved or not. This actually should happen within microseconds. So if I go to a store, swipe my credit card, I want something a response immediately. And this is what we usually refer to as event processing, where we actually require response time somewhere in the microsecond range. And those kind of fast data pipelines, they actually require a different model of how to set up our entire pipeline. It's not sufficient anymore as in the Hadoop days to just set up MapReduce, maybe set up HDFS and everything was running fine. We actually need a more elaborate pipeline for this. And this is the so-called fast data pipeline. And it typically looks like this. On the left, we have some event generation. So this could be, for example, me swiping my credit card here at a store. And then we have an ingestion system. So typically, we don't want to send the events directly to our analytics layer, but we want to have some buffer in between, which can also help to route information or even to persist information. And typically, there Kafka is used, for example. Then at the middle, we have the core part, which is our analytics layer doing the actual work and processing. So this is where we answer all the questions where, for example, the question whether my credit card transaction might be fraudulent and should be denied, or whether it's actually an okay transaction is answered. And most likely at the end of those processing, we actually need to store results as well. So we need some kind of storage layer. And then at the end, we also want to react upon whatever happens. So for example, my credit card transaction being declined or approved, this has to be acted upon and somehow transferred back to the store so that I can actually leave and have paid for my whatever I bought there. And a typical implementation of this is the so-called SMAC stack. So SMAC stack actually stands for Spark, the S. The M stands for Mesos as kind of the underlying layer connecting all of those different systems together. A stands for Akka, which is a very convenient way of building those distributed actors acting up on whatever decisions have been made in the analytics layer. The C stands for Cassandra, being the storage layer, and the K stands for Kafka, being the ingestion layer. What I still find important, and which we're also going to see throughout this presentation, is that those are just like typical instances. So usually when I refer to the SMAC stack, I don't necessarily talk about those specific instances of applications, but I usually more refer to this typical pipeline we see on top. And we'll see different alternatives to, for example, using Spark or using Cassandra in this pipeline. What does it mean for our data center? So data centers, they have also grown and they need to adapt to this kind of new workload. As mentioned earlier, back in those days where we had Hadoop, it was rather simple because it was simply our Hadoop cluster running there. Nowadays, when we have all those different tools, potentially also some microservices running there, it becomes more complex because we have a lot of different applications competing for access to our cluster, competing for resources in our cluster. So each of those applications would like to own the entire cluster, but as we have different applications, we actually need to share the cluster in between. And the naive approach of doing so, which we still see when going out in the field quite a lot, is actually to partition your cluster into subclusters. So for example, you would take the first 4 nodes and make it your Spark or Hadoop cluster to do your analytics. You would take the next 3 nodes and make it your Kafka cluster. You would take another set of nodes, maybe install MySQL there, or a distributed version like Galera cluster. You might take another set of nodes to run your microservice. And this approach has multiple disadvantages. The biggest one, in my opinion, is the operability. So an operator actually has to go in, he has to maintain those different subclusters. Imagine one of those nodes in the subpart of where your microservices are running is failing. Now the operator has to step in and move resources that actually the microservices remain up and running, because most likely this is going to be the user-facing part of your cluster. So it comes with a lot of operational overhead and manual management. The second disadvantage is that usually we end up with pretty bad utilization rates of our cluster, because each of those subclusters we need to provision for the maximum workload. And that means that in each of the subclusters we're actually wasting resources. So this was kind of the vision back in 2010, 2009 for Apache Mesos. And the vision is to actually view the entire cluster as one big resource. So to not treat it as individual nodes, but basically just see the entire cluster as one big pool of resources. And that actually means we're not saying run Spark anymore on nodes 1 to 5, but we simply say, I want that many resources dedicated to Spark. Oh, and by the way, if one of those nodes where Spark is running does fail, please schedule it somewhere else. And I usually like to compare that to my laptop. I mean, in my laptop, I hopefully don't have any failures like this where CPU is failing and something would be severely off. But in general, right now, I don't care on which core on my CPU this presentation is being rendered. I simply want that Keynote is working and showing my presentation, that somewhere in the background the webinar app is running, and that later on my web browser will show you the cool demo we have prepared. So I don't really care where it's running, I simply want that it's running, and Mesos kind of has the vision of providing the same for your data center. Apache Mesos is actually an Apache top-level project, and I usually like to refer to a cluster resource negotiator, which basically means that it's taking care of all the underlying resources and hence aggregating them into this big pool we just talked about. It's actually being used by a large number of large companies. So, for example, if you ever use Siri, you've used Mesos underneath. Twitter is being built around Apache Mesos, Airbnb. And this is actually quite nice being an engineer there, because you know that your code is actually running on clusters with several 10,000 nodes. From an architecture point, and this is actually why it's so well suited to those fast data stacks, it employs something called two-level scheduling. And two-level scheduling actually refers to the division of labor between the so-called framework schedulers and the so-called Mesos resource scheduling. So Mesos itself only cares about resources. So Mesos itself doesn't really care which tasks are started there. And this is up to the individual schedulers. So imagine, for example, a Spark scheduler. A Spark scheduler is getting a resource offer from Mesos. So basically, Mesos is going to ask, hey, Spark, do you want to use 5 CPUs and 10 gigabytes of memory? And then Spark can say, yes, sure, and I want to start these and these jobs there. Similarly with HDFS, which might have totally different requirements and what kind of offers it wants to accept and where it wants to run. So this is kind of the idea that you can encode the application-specific logic into those framework schedulers and have the more general part, which is basically dealing with the resources. This is what Mesos itself will take care of. And this is especially relevant if we are talking about stateful services, as for example, Cassandra, as HDFS, which need to store some state, because in those scenarios, it's often very vital in how you recover from errors. Imagine, for example, there's a name node failing, or even 2 name nodes failing in HDFS. All of a sudden, you need to recover the data from your journal nodes and then restart your name nodes. And this is something you can easily encode into those framework schedulers, but it's nothing so general that it should be included into the Mesos logic itself. DCOS. So DCOS stands for Data Center Operating System. And DCOS is basically a distribution of Apache Mesos. So it comes with a GUI, it comes with an app store, it comes with security, it comes with a default scheduler. So basically, it brings everything you need to run Apache Mesos in a production-like environment. If you've seen the slide before where we talked about all the companies running Apache Mesos, those are often like very large companies as Apple, as Twitter, and they have dedicated engineering teams which can actually build similar tooling around, or which have built similar tooling around. And DCOS is the idea is that not everyone needs to do that, and we have a default set of tooling around Apache Mesos to deploy and run it at scale. And by doing so, we actually gain a lot of flexibility in both what we can run on top. So we can both run those big data applications, those fast data applications we've been talking about. We can also run microservices and containers. And also to the bottom layer, it gives us flexibility that we are not tied into any specific cloud provider API, for example. We can easily switch between an on-prem cluster running in my own data center and, for example, a cluster running on AWS. And we could also switch back if we decide that our own data center is more efficient, for example. So we are not tied in to any specific infrastructure here. And again, similar or same as Apache Mesos, DCOS is also open source. There's an enterprise version, but the core part, so everything you need to run it, is actually open source as well. Okay, having that said, so having discussed this bottom layer Apache Mesos, which is gluing all those different technologies together, let's go back to the actual SMAC stack and let's recall that actually it's more about the pipeline and not so much about the individual technologies. And how that works out, we'll see in those middle layers, so ingestion, analytics, and storage. And let's kick it off with ingestion. So ingestion, the typical example, and this is also where the K in the name comes from, we would use Apache Kafka. But we have a number of different options. So there's, for example, RabbitMQ, there's FluentD, Logstash, Akka streams. So we have some choices if it comes to message queues. also, if we are running in a cloud environment, also those cloud environments, they offer their own implementations. So, for example, the simple queuing service in AWS or Google Cloud has a similar offer. The cloud-only ones, this is maybe the only ones where I would recommend to be very careful when using them, because they actually tie you into their APIs. So once you're using AWS Simple Queuing Service, it's really hard to switch back to something else because you might have coded your entire application, your architecture against it. All the other tools, they have valid use cases. And so, for example, the default one, Apache Kafka, and that is usually also my first choice if someone asks. It's kind of a really high throughput distributed system. So what's nice about it is that it scales to very large clusters. And I have a very simple concept called topics and pipes. So topics are basically named pipes and which a producer can write data into and from where consumers then can consume the data. So I could, for example, have multiple topics, and we'll also in our demo later on, we'll see how we can create multiple topics and utilize them. The nice thing, which allows a very flexible architecture by using Apache Kafka, is that actually those topics or messages, they are buffered and persisted. I can kind of control how long it should be persisted, but that, for example, allows me to have multiple consumers to one topic. Imagine, for example, that you have multiple groups, you have some kind of streams. Let's take the credit card example again. So you have your stream of credit card transactions, and you have one team which actually needs to decide whether those are okay transactions or whether they should be declined. And you have one other team which wants to run like more analytics on it, so gathering some statistics at the end of the month, at the end of the day. And you could actually have two consumers, one using something like Flink for the really fast decisions, and another team listening to the same topic using something like Spark to do those statistics at the end of the day, at the end of the month. So this is very nice that you can actually consume, have multiple consumers for the same data set. FluentD is one other example. FluentD is, for example, very targeted to treating log files and distributing log files to then different backends. So it has a similar promise that I can have multiple producers producing log files and then actually multiple consumers which can gather log files from there and either archive them or create some alerts. So it's similar, it's not quite as scalable, and it's more targeted to the specific use case of log files. So with those big set of different tools, how do you actually choose whichever one works best for you? And basically comes down to the types of messages you're using. So are you producing log files? Are you producing event data? And then also scalability is usually a question. And you shouldn't just say scalability, I want to scale infinitely. You should have a reasonable assumption to what number of messages your system will scale. Because if you're having a very small kind of load and you don't expect it to grow too fast, you can actually save a lot of resources by not having to scale your cluster to very large sizes. The other thing, and this we're going to see in more detail, is the delivery guarantees, because they actually have an impact on how you have to code your application around it. And then routing capabilities, so how complex do you need the routing to be? And let's just start by looking a little deeper into delivery guarantees. You have three kind of models which you should consider or have to consider when choosing them, and then also when coding your application against it. The first one is at most once. So that means if I put a message into such kind of queue, which is supporting at most once semantic, the message might be delivered, but it may also be lost. The only thing I know for certain is that I'm never going to receive it twice at a consumer. The guarantee we would actually all like to have is it exactly once. So exactly once would be I throw in a message and I'll have exactly once having a consumer consume it. This is unfortunately very hard to achieve in distributed systems because anything can go wrong. So any system claiming it has exactly one semantic, there's still certain failure scenarios where I won't have exactly one semantics because the error, a node failure, for example, might just occur in that instance of time where between persisting a checkpoint or doing some other work that I actually will either receive it once or won't receive it at all. And the third semantic is at least once, where messages are never lost. So once a producer has written a message into the message queue, it will at least be once consumed by the respective consumer, but it might actually also be consumed multiple times. So in that case, for example, you have to implement some kind of duplicate detection in your application layer or in your analytics layer, for example, by having unique transaction IDs and hence filter them out. The routing. So routing actually is depending on how complex you need to have a relationship between your producers and consumers. What Kafka supports are simple pipes. So you can really just imagine that being a pipe, someone is writing data into it, and on the other end, I can attach a consumer. If I use something like RabbitMQ, I can actually have more complex routing where I say, I want those messages going to this consumer, I want these messages being filtered, I want these messages going to that consumer. So often I don't really need this routing capability, especially if we're talking about those fast data stacks. Where I simply want to consume all events, so where I basically treat this message queue more as a buffer in between my event generation and my analytics layer. But in other scenarios, I might actually need more complex routing capabilities. Next, let's talk about the core of our pipeline in the analytics layer. So for processing these kind of data streams, we have a large number of different options. So Apache Storm was probably one of the first ones around. Apache Spark is, as of today, probably the most popular one. Then there is Samza, there's Flink, Apex, and again, those cloud providers, they have their own solutions as Kinesis or Google Cloud Dataflow. As said, Apache Spark, currently it's kind of a default for these kind of processing pipelines. And again, this is where the S in SmackStack actually resides from. And it's so popular because a lot of people already use it for different use cases. So the streaming part is actually just one of the front ends on top of the Spark core. And often people already have coded some kind of batch processing jobs in Spark and are also having operational experience in running large Spark clusters. And the nice thing is I can actually just reuse my Spark batch jobs for my streaming layer, because how Spark actually implements streaming is by so-called micro-batching. So what Spark streaming will do, it will consume a small number of events. So it will, for example, gather 5 or 10 events, and then it will treat it as like a micro batch of data, run its batch job on top of the small data set, and then start collecting this next chunk of this next micro batch for the next round of processing. This is quite nice because it's efficient, but it might actually not be the right thing if I need very low response rates, because I first have to wait for 5 events to be gathered and then the analytics will kick in. And if I, for example, have the example of credit card data, I don't want to wait for 5 or 10 transactions to accumulate until I start doing the analytics on it. And so how do I choose between all those models? As we just discussed, there's the execution model itself. So do I have native streaming where I would process each tuple individually, or do I do microbatching? And usually the execution model also has implications for the fault tolerance granularity. So if a node fails during processing, how much data do I actually have to recompute? And again, there are also delivery guarantees tied to those kind of system, delivery/processing guarantees. So how often does it might it process an individual tuple? Going back to the execution model once more, as said, on the one hand, we have microbatching as implemented in Spark, where we're going to process small chunks of data, or in native streaming, where we actually process each tuple individually, which might be better suited for scenarios as, for example, credit card transactions. So basically, always when I care about individual events being processed immediately, then I want something as native streaming. If I don't care so much about response time, then microbatching is a pretty good choice because I have efficiency and I can actually reuse my batch jobs if I'm using Spark. This kind of model also has implications on the fault tolerance. So what happens if there are errors in between? And there's 3 kind of potential implementations for this. So first of all, I can actually acknowledge each individual tuple which is going through my pipeline. So this is, for example, what Storm is doing. It, of course, this adds a lot of overhead because I need to write a persistent checkpoint for each individual event. Hence, to make this more efficient, what Flink or, for example, Apex are doing, they're considering a checkpoint per batch. So even though they are processing each tuple individually, they only checkpoint per microbatch again. So if a node fails, they actually have to reproduce a small subset of events. So basically the last microbatch which hasn't been checkpointed yet. And Spark, as they are doing microbatching anyhow, they also just checkpoint per microbatch, obviously. Delivery guarantees, similar as with message queues, you should be aware that exactly once still has certain failure scenarios where this isn't true. But in general, for example, Storm is just guaranteeing at least one semantic, so you have to be aware that you might process an event multiple times in your job, and hence your application layer needs to be aware of that. The next layer we would look at is actually the storage layer. And looking at the different data stores around, it's actually even more complex or more choice than we see layers before. And it's even growing nowadays when I see like every day how many new data stores or how many new file systems there are for container storage. Something I find really exciting if we're talking about container storage is that we are starting to develop certain standards there. So CSI, it's called Container Storage Interface. And I think this will even make the growth or explosions of systems which support storage for specific containers even more easy to implement, and I believe in the future we're going to see even more different implementations. So how do we choose between them? Probably the first choice you should be aware of is the data model. If we are coming from a traditional world, we usually used to relational data stores such as Postgres, supporting foreign keys, joins, and fixed schema. If we are moving to this more distributed world, for example, talking about Cassandra, we usually talk about different data models. So for example, Cassandra, even though it might look like a relational store, and with CQL you can actually use it as such, at its core it's actually a multi-column key value store. And this is something you should be aware of First of all, when migrating your data over there, and secondly, when also writing your queries. So, for example, Cassandra, if you're just porting the same queries you've used for Postgres before, they probably are going to be pretty inefficient, because Cassandra is good if you're querying an entire column of data, but it's not so good if you're, for example, doing a lot of joins across different columns or different tables, whatever you define as table in this sense. So you should actually be aware of the data model and adapt your data layout and your queries accordingly. Graph is another kind of model which allows you to model complex relations, as for example a social graph, or anything having like tight interconnections in between different nodes. So it's often used for recommendation systems, or for example also for fraud detection, where I'm building like a net or a graph of where my credit card has been used, or what kind of transactions I like to do. Next, we also have a document store, which is kind of a schema-less variant. So if I have, for example, store information about people, which might vary a lot between different data sets, because, for example, people have different hobbies, and for each hobby we want to store extra information specific to that hobby. It's kind of, it doesn't have a fixed schema, but it's just semi-structured. And their document is usually a very nice structure supporting that. So, for example, a product catalog or session data is a good fit for a document store. As we're talking about events, so often we also have sensor events. So imagine a plane where each engine is generating multiple terabytes of data during a flight. And this is something very specific, because it's the same, it's very, like those values, often they don't vary much, and it's like the same data point over and over again. It's like a temperature reading 100,000 times repeated. And there's something called time series store, which, for example, Prometheus has at its back, or InfluxDB support. And they offer a lot of compression rates, and hence efficient queries and efficient storage of such kind of time series data. And then, of course, we also have file storage, which for most people know HDFS. There's also Kilobyte or Ceph, which supports like this more traditional notion of files in my distributed system. Now, I would actually, we talked a lot about those different pipelines and about the SMAC pipeline. Now I would actually like to show how this can be set up in practice. And we're going to look at fraud detection, not with credit card data, but with transactions. So if I'm transferring money from one account to the other, there are certain regulations that once it hits more than $10,000, it actually needs to be looked at and treated differently, because there's potential for money laundering. So what we want to detect in our demo is multiple transactions between two accounts summing up to more than 10,000 US dollars. So if, for example, I have a transaction from account A to account B for $5,000, and then I have another one from A to B for $6,000, then this is something where I, as a bank, I need to look at, and I want to be alerted, and this is what we'll detect in this demo. On the left, generating the events/transactions is a data generator, which is generating exactly this format: transfer 5,000 euros from account A to account B. And these are actually written into Kafka topics, being the ingestion layer. And then as the stream processor, we actually use Flink in our demo here. The one thing where we diverge a little bit from the traditional SMAC stack is that we actually also use Kafka for storage. As said, Kafka also supports kind of persistent storage in its topic, and so the output of Flink is written again into Kafka, and our fraud display, which is then the actor, can pick it up again from the Kafka queue. So having that said, let's actually switch to our cluster. And I've started a DCOS cluster here before. And as we can see, there's nothing running. We have 6 nodes connected, but my resource consumption is pretty empty. So DCOS offers something called the catalog. And the catalog is basically the app store for your cluster. And I can simply go in here and, for example, install Kafka. So I go here, and now I'm deploying Kafka. And as we can see, now it's staging, which means it's probably pulling the resources it needs to start and starting up a Kafka cluster. We also need Flink in our scenario, as we want to do some stream processing using Flink. So I'll actually go here and also deploy Flink. We can see that both are deploying. And if we look at the dashboard, we actually also see that resource consumption is going up because step by step they're actually using more resources. And we can already see Kafka is healthy. So if we now go back here and take a look at the Kafka, we see it's has started the first broker. So we could actually start assigning and creating topics and writing data into those topics. And now we see that actually the second broker is also started up. And so step by step, we are building our Kafka cluster here. As our Kafka cluster has actually started, let's take a little look. This is also integrated into the CLI. And so I can now do DCOS Kafka. And let's first look at the endpoints. As mentioned earlier, the idea is kind of that I don't have to specify where something is running in my cluster. I simply say I want to have that many broker instances. This now gives me the challenge that I actually need to figure out where my brokers are running. And the nice thing is that I have multiple ways of addressing my brokers independently of those addresses where they're actually running. So first of all, what will happen in the background is that we generate DNS names for each of the brokers. So I can use those DNS names to reference my brokers and talk to them. So when, for example, Kafka broker 0 would fail over and be restarted on a different node, then I can still reference it using the same DNS name. We also have an automatic load balanced address for all brokers. So if I'm using this address here called virtual IP, I basically can talk to all brokers in a load balanced fashion at the same time. So this makes it really convenient to talk to all different tasks. So a typical pattern in this distributed world is that I have multiple instances. So for example, multiple web servers or multiple API servers because I need to scale out. And such kind of load balanced address is a very easy way of doing that. Next, I actually also need to create the topics we've been talking about before. So I also can do that here from CI. So DCOS Kafka topic create, and we need 2 of them. The one is called fraud, where we would actually persist whichever fraud we detected. So let's generate this. And the second one is transactions, which is where we generate the initial transactions into. So where our data generator will write the transactions into. Great. We could also have a look. Topic list. And we should see, yes, we have 2 topics created. Great. Switching back to the UI, also Flink is up and running. And let's have a look at the Flink UI. So we can go here to the Flink UI. Flink has a similar integration in the CLI, but for now, let's actually use the UI because I actually like the Flink UI quite a lot. And let's upload our job jar. So here, let's upload. And this job jar, it basically contains the job we want to run. And if we want to take a short look at it, by the way, all this code, it's open source. So if you want to have a look, there's a GitHub repo called github.com/demos. It's also on the slides. So if you want to run this yourself, or if you want to look at the Flink job yourself, feel free to go here. So if we look at, it's called financial transaction job, and all it does is it consumes from a Kafka stream here. It will rate and aggregate on a sliding window, and basically keying by the original account and target account. Recall that we want to detect amounts over $10,000 being transferred from one specific account to the other, and this is why we key by those two fields here. And then at the end, we filter if the transaction amount in this aggregate is over $10,000. And if this is the case, then we actually output it to our Kafka sink, which is our fraud stream fraud topic we just created. So hopefully it's uploaded, yes. And now we can actually start our Flink job here. So let's submit it. And now we already have our Flink job up and running. So here's our source where we consume the data from our Kafka queue. And then here's the trigger window we just saw in the code itself. Okay, the last two parts, if we recall our pipeline, which are missing, is the actual data generation and then the display. And again, we can deploy it from here. So this again is the demo repo I checked out. So let me deploy TCOS Marathon app at, and first of all, the generator. And here we have a JSON file, which basically describes how to start this job. And we already started the deployment. And I'll also add the actor, which is our fraud display.json. Great. And having done that, let's have a short look what that actually looks like, what we just deployed here. Generator.json. So those generators, it's a simple Go program. And the nice thing about Go program is that I don't need anything to run it. So I can simply start it without having to generate a container image. All I have to do is I pull the generator, the binary, and then I run the binary, and I pass it the broker command we saw before. Okay. So let's have a look whether all of this is running. So yes, it's all up and running. And now let's have a short look at the logs here. So to see that it's actually up and running. Yes, we can see we're writing things into our stream. This looks good. Great. And let's also have a look at the fraud display. Usually it takes a while to start up and detect fraud, but here we can already see that we detected the first transactions summing up to more than 10,000. And so, for example, here, if we look at the first one, the transaction aggregate, it started at timestamp 0, it ended at a later timestamp, and it's transferring from account 5 to account 2. The first transaction was $2,827, and the second one was $9,721. And so together, this sums up to more than 10,000, and so we detected potential fraud here. So this is a very simple demo of how to set up such kind of systems and how to utilize something like SmackStack. If we switch back to the slides here, let me actually mention a caveat which I don't like about demos in general. And this is that typically people feel after having deployed such demo that it's really simple and how to set up such things. But you should keep in mind that the hard part actually comes up afterwards. And this is how do you keep such systems up and running? And there's things you should consider are, for example, configuration upgrades. How do I add more Kafka brokers? How do I reconfigure the names of my Kafka brokers? Binary upgrades. So how do I switch to the next Kafka version? How do I switch to the next Flink version? Cluster maintenance. How do I actually upgrade the cluster itself? So how do I switch from Mesos version 1 to Mesos version 2? How do I switch from one DCS version to the other? All while not affecting the users or actual workloads running on top. Because if this is, again, our credit card example, I don't want that during a cluster upgrade, no one can use his or her credit card. And key part also of keeping a system up and running is monitoring of the entire operations and metrics in the cluster. So typically, for example, for those JVM-based applications as Flink, as Kafka, monitoring garbage collection is something really helpful. Monitoring response times is another very crucial thing everyone should do. And I should also evaluate how I can actually debug runtime blockages. So what is a practical way of also scaling that? For example, do I have to give everyone in my engineering organization SSH access to the production cluster to debug something going wrong there? Or do I have another way of doing that? And also service operations, this is something you should consider before implementing such kind of system, because it becomes really, really difficult if you do that once such kind of pipeline is up and running. All right, and this is actually the end of this presentation, but as mentioned, I'll be in Milan in pretty much a month, yes, a month from now. And so I hope to see some of you there. And otherwise, let's see whether there were any questions in the channel here. Let's switch to questions. So feel free to type in any questions or even unmute yourself if you want to ask interactively. Okay, otherwise, thank you very much for listening. The slides and recording will be available. And if you later on have questions, feel free to hit me on Slack, ask me at CodeMotion Milan, and see you there. Thank you.